All right, so today we're going to look at section 1.2, which is on using the graphing calculator to solve different kinds of problems. So I'm going to show you how you can find an intersection point on the calculator, and a little bit more with zooming in and out. So first thing we're going to take a look at is just what I call, it's a general problem solving process. So not even specific to math problems, but just any kind of problem. So first thing you always want to make sure you can figure out when you're reading a problem is what is it that they are giving you in the problem that's going to help you solve it, and what's the question they're asking you to find. So if you're not sure what the question's asking you, then you're definitely not going to know how to come up with an approach to solve it. Now, once you know what it is you're being given and what it is they're asking you to find, then we have to come up with some kind of plan to solve the problem. What's a strategy that we use a lot of times in math when we're trying to solve a problem, especially like a word problem? A lot of times you have to set one of these up with all the information they give you in the word problem. Yeah, an equation. So a lot of times we have to figure out what's going to be the equation we're going to use. Now, if I was asking you a problem about like area of a circle, that's a well-known equation. You can just go in a book, any math book, that has geometry in it, and you're going to be able to find the area formula for a circle. That's not a formula you need to invent. Sometimes when you're doing a word problem, the formula you need to figure out is not a standard formula. It might be something very special to that problem. So then you have to figure out your own equation, right? So equations. What's something else that we might do with a word problem to make it easier to see what's happening in the problem? Yeah?
Eliminate unnecessary information.
Okay, you can eliminate some things or highlight the important things, so that's always good. So yeah, kind of identifying, that would kind of fall under identifying what's being given. Maybe you underline things that are important. But what would you do with all that given information? Let's say you had a lot of sentences in the word problem, and it's hard for somebody to kind of think about what's happening when they just see lots of sentences. You could take all that information, and maybe this is something you'd have to do before you even turn it into an equation. Yeah?
Like highlight or circle all the important parts.
Yeah, so you can do that. Yeah?
Like put all the numbers just separate from the word problem, like write them out.
Okay, so you want to definitely start to do something separate with all the information. What would make it easier to kind of see what's going on in the problem? Yeah?
A graph.
A graph, yep. So maybe a graph, or in general, what's kind of more general, but a graph is kind of an example of it. Yeah?
Like a general diagram of
Yeah, some kind of diagram or picture or sketch, right? Like if I said to you, you've got a building that's 100 feet tall, it's casting a shadow 50 feet long, the sun's at an angle of X degrees, calculate something, right? There's a lot of information there, but it's going to be easier to see what's happening if you draw it up. Another approach, a list. Okay, that can be helpful. Like if I said to you, I want you to take the letters A, B, and C and tell me all the different ways you can arrange them. ABC, ACB, BAC, BCA, CAB, CBA. There's 6 different ways. Well, that worked okay for 3 letters because there was only 6 different ways I can do it. But what could happen that wouldn't be very practical with a list? Yeah?
Can get too long.
Yeah, it can get too long. So if I said to you, I want you to take every letter in the alphabet, use them one time, and tell me all the different ways you could possibly arrange the letters in the alphabet. Well, the question wasn't to list them all. The question was to tell me how many ways are there. So if you can figure that out without a list, it's going to be much better because there's way too many possibilities. And then the last approach, solving an equation, we just talked about that. So now, once you figure out what's being given, what it is you need to find, and you've come up with a approach you're going to try, now you actually want to do that. Okay, so now maybe if it's solving an equation, we actually follow through and do that. That could mean maybe if it's a quadratic, you do factoring, or you do the quadratic formula. But you've got to figure out how you're going to carry out your plan. If it's making a picture, right? Are you going to draw a picture by hand? Are you going to use the graphing calculator to maybe help make a sketch? Whatever tool you're going to use, now's the time to get that tool and do your plan that you came up with. So we're going to look at an example, and we're going to do it by hand with algebra, which is probably going to be faster, and then we'll do it as a picture. So we'll try two different approaches. So in this problem, a company charges $15 to rent a car and 20 cents for every mile that you drive it. Now, they're not giving us a choice about what approach they want us to do. They are saying equation. So that's what we have to do to start it. When you write an equation, what in algebra is usually in an equation a lot of times? Yep. Julia, were you using it? Yeah.
A variable.
Yeah, variables, right? One or more variables. So we've got to decide how many variables we need and what their names are going to be. Okay. Anybody have an idea of how many variables, or if you think it's just one, you can tell me one variable, how many variables you'll need in this equation? Caleb?
2.
Yeah, you're going to need 2. Can you tell me what your first variable would represent?
The amount of money needed to rent the car.
So, yeah, the amount of money that it costs you to rent the car. Yeah. And what about the second variable? Yep.
How many miles you're driving?
Right. How many miles you're going to drive. Now, what are 2 common letters we use for variables?
X and Y.
Okay, X and Y. If you use X and Y, one of them is usually independent variable, the other one is the dependent. We have to stick with that convention. Okay, we got to do that just like it always is. Which variable is also known as the independent? The X or the Y? Yeah?
X.
X, very good. X is the independent, Y is the dependent. Now you've got to figure out in this problem which one is independent. Is it mileage or is it cost? So one of our variables is mileage, the other one is an amount of money. Anybody think they know which one is going to be the X, which is the independent variable? Those?
Amount of money. 50.
The amount, well, the 15, that's just an example of an amount of money. But in general, the amount of money to rent the car could be any amount. It could be $100, $600. But no, money is not going to be the X. Yeah.
It would be the 20 cents because total cost is determined by how many miles you drive in the end.
So the X variable would be what?
So the way I wrote the equation, it would be 20 cents in parentheses X, then plus 15.
And what did your X stand for?
The amount of miles.
Yes, the amount of miles. So X is going to be the number of miles that you drive. And if you're not sure which variable is X and which is Y, what I do is in my head, I make a sentence and I read it both ways and see which one makes sense. First thing I say is, does the cost depend on the number of miles I drive? Or does the number of miles I drive depend on the cost? It's the first one. The cost depends on how many miles you drive. Right? If you walked into this car place and said, how much is it going to cost me to rent the car? The person would say, it depends. Depends on how many miles you drive it. So the cost is dependent on the mileage. Cost is dependent. It's the Y. Miles is independent. And there's other names if you've heard domain and range. We're going to use those terms a lot. But I just wanted to introduce independent and dependent. A lot of times money is usually the dependent. Like if you work a job where you get paid by the hour, and you said to my boss, well, how much is my paycheck going to be next week? They say, well, it depends on how many hours you work. Like the amount of money is dependent on the number of hours you're at your job. Okay, so a lot of times money is dependent. All right, so now we want to make up an equation. And I think, was it Boris, you already said your equation. Can you just say it again?
It was the 20 cents, parentheses, the x, plus 15.
Plus 15. Yeah. That's the equation that represents the cost as a function of how many miles you drive the car. So 20 cents times the number of miles, plus that $15 fee, that's a one-time fee. Maybe that's the fee you pay to book the car, like depositors. Any questions on that equation? Okay. So now, that equation we just came up with, sometimes our book will refer to that as like the equation, or they'll call it the model for the situation. That models what's happening. I want to use that model to find the cost for 50 miles. Okay, so how would I use that equation and the 50 to get the total cost? Yep, Dylan?
The 50 miles are variable.
Okay, so the 50 is going to get plugged in for what variable?
Okay.
Yeah, you're going to take the 50 and you're going to fill it in for the x. So we've got 20 cents, 0.2, times 50, plus 15. Okay, what's 0.2 times 50? 10, and then 10 plus 15? 25. And what do we want to put for a label on that? Because it's dollars, because it's cost. Yep. So there's the cost to rent the car if you drive it 50 miles. Now, the next one, if we drive it 100 miles, could we just say, oh, double the mile, double the cost? It's going to be $50. Would that work? Why not? It sounds reasonable. Double the miles, double the cost. Yeah, Jack?
Because the 15 is not doubled.
Yeah, you're not supposed to double the 15, right? You're only supposed to double the mileage part of the bill, not that one-time $15 fee. So a lot of times when you see a problem, you might think to use some logic that makes sense to you, double the miles, double the cost, but sometimes that simple kind of thinking doesn't always work. Okay? So you have to be careful. So we have 0.2 times 100 plus 15. What's 0.2 times 100? Yep, 20 plus 15, 35. So if you drive the car 100 miles, it would be $35. Okay. Any question on those two? So that equation, you can call it an equation, you can call it the model. It's basically an algebraic representation of the problem. If somebody were to come in right now and they looked at this on the board, they have no idea that that's about renting a car. They don't know the context for that equation. So the pure equation itself is called an algebraic representation. Now, I want to use that algebraic equation one more time, but I want to do something a little different. So now it says Sarah was charged $50 to rent the car. How many miles did she drive? What's different about that question compared to the previous two questions we just did? Yeah, see?
They gave you the total instead of they gave you the total and asking how many miles instead of giving you the miles and asking for the total.
Right, so it's exactly the opposite information. They're giving you cost, and you are now finding mileage. what would I do with this 50 if I want to find
Minus
Mileage.
15 from it.
how? Let's say somebody doesn't understand that. I know what you mean, but how would you figure out that you need to minus 15 from it?
That's what she was charged for, so she would minus the 15 because that's what she paid just to initially rent the car. And that would give you 35 miles, and that's when you would divide it by 0.2 to get how many miles you drove.
Yeah, so all those steps are perfect. That's the exact reasoning you want to do. Now, if somebody couldn't figure out those steps, how could you explain it more algebraically if they're used to seeing like equations? But that's the right thinking, and it is the steps we're going to do. But let's say they need an equation to figure it out. Yeah?
Put it where y is.
Right, just take the 50, plug it in for where y is, and we're going to end up doing exactly what Sam just said. So you plug in 50 equals 0.20x plus 15. Actually, I think I have more space down here. Yep. And what did we just say the first step was to get x by itself?
Minus 15.
Yep, minus 15 from both sides. So that leaves you with 35. And what was our last step?
Divide by 0.2.
Yep, and divide by 0.2. Again, 0.2, 0.20, it's the same thing. Usually when we do money, we write it to 2 decimal places. That's the only reason I'm doing that. So that cancels out. Now, 0.20, 0.2. 0.2 is 2/10. If you want to think of this number as a fraction, 2/10. What is 2/10 reduced to?
1/5.
1/5. So this is 35 divided by 1/5. Well, dividing by 1/5 is the same as what?
Dividing by 5.
Multiplying by 5, yeah. So dividing by 1/5 means times by 5. So that's our answer. What's 35 times 5? Yep,
175.
175. And what did we solve for?
Miles.
X, and X represents miles. Yep. So 175 miles. Now, just kind of a side note, I'm going to show you on the calculator. If you didn't know that 0.2 was 1/5, you can type in a decimal, press math, go to fraction, and it will automatically convert a decimal to a fraction.
Very cool.
So same thing with something like if you had 0.75. 0.75, if you want to think about it as a percent, is 75 hundredths, 75 over 100. But what is 75 over 100 reduced to? 3/4. So if you do 0.75, math, fraction, it'll give you the reduced version, 3/4. Yeah. Now let's try pi. What did we say about pi yesterday?
It's infinite.
What kind of number is it? Yep.
Irrational.
Yep, it's irrational. And irrational means what? It cannot be written as a fraction. So when you try to take a number that cannot be written as a fraction and change it to a fraction, it just gives you back the same number. Can't do it. Okay? But that is a handy thing. If you ever have a decimal and you need to change it to a fraction, we can use that. All right. Any questions how we got 175 miles using algebra? Now, we're going to try something a little different. We're going to do it with another approach we mentioned, which is drawing a picture. Specifically, this time, the type of picture is a graph. To do it using a graph, I want to go back to what we had at that step. 50 equals 0.20x plus 50. I want to start by focusing on the left-hand side. This is going to get plugged into the calculator, and then we'll focus on the right-hand side. And we're going to plug that in separate. So what we're going to do is we're going to draw two things on the screen at the same time. What's on the left is going to be one. What's on the right will be the second one. So on your calculator, you want to press y equals. And if you have anything already typed in there, we want to clear that out. And we're going to start by putting the left side in the first equation. It doesn't really matter if you put it in the first equation, the second, the third. We just need to put both of those into the calculator on separate lines. Okay, this first one, y equals 50. What would that look like if you draw that? Yeah?
Straight line.
What kind of straight line?
Horizontal.
Horizontal, and it would be at what number?
50.
50. Okay, so right now we've got a horizontal line at 50. We need to keep that in mind because if we do a standard window, that might not be high enough to see that line. Let's go to y2. We're going to type in 0.20x plus 15. Does anybody recognize the format of what we typed into y2? That format is not something random. It's something very specific. Yeah?
Is it y-intercept?
Yeah, it's, well, the y-intercept is part of what that is. And slope is another part of what it is,
I don't know the name of this, but it's y equals mx plus b.
which is slope-intercept. Yeah.
We got the right word.
Yeah, we got there. So that's the slope-intercept form for the equation of a line. And the standard letters that we use are y equals mx plus b. What does m mean in that formula? The slope. And what does that tell me?
Rise over run.
Tells me, yeah, the formula for it is rise over run. And what does the slope look like visually when you draw a line? What does it tell you about the line?
Diagonal.
It could be horizontal, vertical, or diagonal. Could be any of those. But in general, the slope kind of tells you the what of the line. Yeah?
Like, is it like the growth of it, or like the trend?
How it trends. Yeah, another word I'm thinking of that's a little bit more specific. Like, what's the difference between a line with a slope of 0.1 and a line with a slope of 5? Pretend you're walking up that line. Yeah.
How steep it is.
Yeah, it's like the steepness, okay? It's the steepness. And then that number at the end, the 15, what's that?
Y-intercept.
Yep, that's the y-intercept. And what does that mean? It's y-intercept, yep.
Where it intersects with the y-axis.
Right, it's where the line crosses the y-axis. So let's try zoom 6. That gives us a window from -10 to 10 and -10 to 10. Wait for the yellow circle to stop spinning in the upper right. And there's our picture. Okay, where is it? Yeah, it's not here, right? That's not where we're looking. So if we look at our window, let's think a little bit about x and y. What is x in the word problem?
We don't know.
Well, we know what it represents.
The dependent variable.
Independent variable. But specifically, what is that? Yeah?
Miles.
Miles. What's the smallest number of miles you could drive this car? 0. Then we shouldn't be looking at -10. We can't drive -10 miles. What's the maximum number of miles you could drive the car?
As far as
As far as you want. There's no limit. So we could just put in like 75, we don't know. We just put in any number. We're going to be looking for something on the screen though, so we're going to have to see if that number is high enough. Now, what did y represent? Specifically in this problem. Yeah.
Y represented the total, the final total of everything.
Yeah, it was the amount of money you had to pay to rent the car. What's the smallest, well, let's start in general. What's the smallest amount of money that would make sense in any kind of problem? Generally, talking about, like, let's say it was like the price of something. What's the smallest amount of money that something could be? Yeah?
0.
0. It was free, right? You can't pay negative $10 for something. That doesn't make sense. So now in this problem, technically the smallest amount of money to rent a car is how much? Yeah?
15.
Technically it's going to be 15. Okay? But I'm going to go a little bit lower just so we can see the x-axis. And we already have a horizontal line at what number? Yeah? 50. Did you say 50?
50.
Oh, 15. No, that's our y-intercept.
Oh, 50. Yeah.
50, yeah. We have a horizontal line at 50. So we need to make sure we go at least to 50, and we should probably go a little bit more, so it's not right on the edge of the screen. Now when you hit graph, there's your horizontal line at 50, and there's the cost for the car increasing as you drive more and more miles. What do you think we're looking for? We're not solving this algebraically, we're solving it visually. I mean, I know I'm looking for where this equals this, but I need to know what that means on my screen. Yeah?
The part where the two lines intersect.
Right. I'm looking for where these two lines intersect each other. I can't see that right now. If you can't see it, you're not going to be able to find it. So which one of these do you think we have to adjust? X min max, Y min max?
X max.
X max. What would be a good value to try for that? 200. I think 200 will definitely be enough. We already know it's 175. Okay. But if you hadn't done this problem algebraically, you might not know that. So you might have to guess a few different numbers. And that's fine. Now we can see the intersection point. Now, on all of my calculators, you can find that automatically. If you had an older calculator, you might have to press the trace button and just move your cursor till you think it's pretty close, and then read the answer at the bottom. Right? To me, that looks pretty close, and it says 174.2. Well, we know it's not 174.2, it's 175. So how can we get that exactly without just trying to move the cursor and guess? If you press second, and then you press trace, that's going to bring you to the calculate menu. Second, trace. This year, we will use options 2 through 5. We won't be using any of the other options up there. Which option do you think is going to help me to find what I'm looking for here? Yep, option 5. So you can just press 5. And then what it's going to do is ask you 3 different questions. First question is first curve. You basically have to pick a point anywhere along the first thing that you're trying to find the intersection for. Doesn't matter where. We're just identifying the blue one. And you hit enter. Now the calculator knows, okay, use the blue one. The next thing it says is second curve. We're trying to tell the calculator what is the second thing that you want to use for the intersection. We want to use the red one. So you can put your cursor anywhere you want. Doesn't matter. And you have to hit enter. Once you've done that, it'll ask you one more question. It's going to ask you for a guess. In this problem, the guess doesn't matter. Okay? It doesn't make a difference. If you want to practice, you can just move your cursor closer to where they cross. It doesn't really matter where you put it. Hit enter. And you should get an answer of 175, which is the same thing we got right there. Any question on that intersection? So now, it seems like it asked us all kinds of things that weren't even necessary. First curve, second curve, and then the guess. So why did it ask us all those things if we don't really need them? Well, in this one we didn't, but I just want you to watch this one. Let me type in 0.4x. Okay, so now there's more happening here. If you want to find an intersection point, the calculator can only do one at a time. To find an intersection point, you need two different pictures, and you have to see where they cross. Let's say that I want to figure out where the red and the black cross. If I do second calc intersect, the first thing I need to tell the calculator is which two lines I'm using. I can't do all three at the same time. So I said red and black. Right now I'm on the blue. I don't want the blue, I want red and black. If you press the up or the down arrow, it moves you between the different graphs. So if you want to use the black one, press it until you notice your cursor is moving along the black one. And if you have the color screen, the font turns black down here. If I hit enter, I've just told the calculator, use the black one. And the other one I said was red. Okay, I'm on blue again. Now I'm on the red. If I hit enter there, I've just told the calculator, that's the other line. So it's ignoring the blue one. But the guess still doesn't matter. In fact, I could put the guess way over here. And if I hit enter, it still finds it. No problem. Yeah.
When would the guess matter?
So that's the last thing I'm going to show you, when the guess matters. Okay. Let's do something like this. Let's leave the 50, and let's type in, let's try like 0.2x, I might have to adjust this, minus 50 squared. Let's see how that looks. Yeah, that's something. Let's just try x minus 50. Okay, that's fine. Okay, so now let's find the intersection here. This one's going to be a little different. How many intersection points can the calculator do at a time? One. So it's not a matter of first curve, second curve doesn't really matter. There's only two on the screen. I want to use the blue and the red. Blue. And then I can't see my cursor. I know it's on the red one. It's way off the screen because it's at 2500. If I press the left arrow, I can see the Y value coming down. If I keep pressing it, eventually I'll see it come in right at the top of the screen. There it is. Okay, but I just have to pick a point anywhere on the red. And now this is where the guess matters. Because the calculator can only give you one at a time. If you put the guess closer to the one on the right, it will give you the one on the right. If I move the guess closer to the one on the left, it'll give me the one on the left. So the guess matters when you have multiple intersections and you want a specific one. But it will always ask you those three questions. Any questions on the intersection feature? So now that's something on the test. If I said, here's these two graphs, find where they cross, I wouldn't tell you where the buttons are to do it. Because that's something I'm seeing if you remember how I taught you to do it. All right, so this window that we found, that was a really good window. Okay? It showed everything that's important. This is a good window too. If the goal is to figure out where the parabola crosses the blue line, yeah, I can see it perfect right there. That's a good window. When you have a window that shows you everything that's important in the graph, that is called a complete graph. So if you see in the homework or on the test, the directions, find a complete graph, all you have to do is tell me the window you used. You don't have to draw anything. Tell me the window. X-min, X-max, Y-min, Y-max. And there's not necessarily just one window. There might be more than one window that shows everything that you're looking to see. Yep.
Are the tests open now?
For the test, you can make a reference sheet. So you can't use your entire notebook, but you can make a reference sheet. Yeah. I don't think I said that yet. Yes?
Is that for all tests or just this one?
Generally, for all tests, I don't think we have any that they're not. Midterm and final, that's the same thing, one side, but there's a lot of information, so yeah, still one reference sheet. Right. So what would be a bad window for this? Okay, if I'm looking for where the line in the parabola cross, this is not a good window. Because all I can see now is the parabola. I've lost the line. That's not a complete graph. So what does important mean? Well, it depends on the graph. If you're looking at a U shape, probably the bottom of it, like the vertex. Every graph is different. So you're going to be able to see the whole thing. Everything that's important. Obviously, a parabola goes on forever, so you're never going to see the whole thing. But if you see a U shape, then that's what you're looking for. So I think we did one like this yesterday, but let's try this. Let's graph y equals x squared plus 10. And I'm just going to use the window that I already have in here from the last problem. I think I changed mine a little. Your window is at 60 still. I think I changed mine to 40. But that's fine. You could just leave your window the way it was for the last problem. Type in x squared plus 10 and hit graph. Okay. Is that a good window? No, that doesn't look like a parabola at all. Parabola, I should be seeing some symmetry, and I'm not. So then let's reset it and do zoom 6. Let's start over and see if that's a better window. Okay, how's that window? Well, it's even worse. Now I don't have a picture at all. So what value needs to be adjusted because of that plus 10? The y what?
Y max.
Y max? All right, what do you want to try?
50.
50. Looks good to me. Now you can see the bottom of the parabola, that's the vertex, and I can see it's curved. That's a great window. 50, 60, 40, 30, any of those would be fine. What I wouldn't do for y max is like 500,000. Because then the parabola is going to look like a flat line. Because you zoomed out so far, you can't even see it. All right, so what did I tell you to write down? The window. Let's take that. Down there. I want you to write down those two and those two. Any question on that? All right, so last one. I'll just mention what this is called. What is that shape called that we just drew? Yep, that's a parabola. So if you didn't know that, you probably want to write that down. Now, it was a simpler parabola. It was just x squared plus 10. It didn't have anything making it more complicated, but it could. And when we add in more, it can change how wide it is, and it can move it left and right, up and down, all kinds of things. But we did graph a relatively simple parabola. Now, that's a quadratic equation has the squaring function. What function is related to squaring? But the inverse side. Yep, square rooting. So now we're going to draw a square root function. Yesterday I mentioned different categories of numbers, and basically what was the biggest category of numbers that we talked about? It included everything.
Real numbers?
Real numbers. When I do this problem, I want to make sure that this is a real number. So think about a square root in general. Think about what goes right there. What kind of numbers do you want to avoid? Because if you put them in that circle, you will not get a real number. Yeah?
I mean, negative numbers that are bigger than 20, because if you put a negative and change it, you have to make it accurate.
Okay, so yeah, so forgetting about that one for a second, we just, in general, yeah, we want to avoid having negative numbers right there. We do not want negative numbers here. So what does that mean we do want? We don't want negatives. It means we want what? That's most of it. What else do we want besides positives? Yeah, all positive real numbers, but that's saying all positives is not the opposite of all negatives exactly in math. Like if you say you don't want negatives, it means you want, this is kind of a math thing, yeah?
Whole numbers?
No, decimals and fractions are okay here. Yeah?
0 and up.
You want 0 and up. So the opposite of a number being negative is 0 and up. If you just say positive, you've left out 0. Okay. So you want this to always be 0 and up. Plus, if you want that to be guaranteed 0 or higher, then that means you want x, if you move it to the other side, to be negative 20 and up. That's what x has to be in this problem. If you plug in a number that's not bigger than negative 20, you plug in negative 30, right? That's smaller. That's not going to work. Is there any question why you could only fill in numbers negative 20 and up right there? So now let's graph that square root. So let's go to y equals. Clear out anything else you have. Square root of x plus 20. And let's do zoom 6. Zoom 6. Now I will tell you that a square root function is curved. Is that a good window? Knowing what I just told you. No. To me that looks almost like a straight line. Pretty straight. We've got to adjust our window so we're seeing everything that we should for the x's. What's the lowest that we're going right now for the x's? Yeah.
Negative 10.
We're only going to negative 10. How low should we go if we want to see all the values that you're allowed to plug in? Yeah?
Negative 20.
We should go to at least negative 20. And I'm going to go just a little more so it's not on the edge of the screen. I'm going to do negative 25. Now, let's hit graph again and see if you can tell that it's curved. Okay. So what do we think now? Can we tell that it's curved? Or does it still look like a straight line? Yeah, definitely. It's got a curve to it now. Put it here, make it a little bigger so people can see it. What you were looking at before was basically a small section like that. Yeah, that section looked pretty straight. But when you go all the way back to the beginning of it, you can see it's curved. Square root functions always have a start point, and then they curve in one direction. Do they always curve to the right? No. You can change them so they curve in any direction. Those are basically the pattern you would see for the 4 different kinds of square root functions. And the other thing I can show you is if I put a negative in front of all of that and graph it, what does this look like now? Yeah, it looks like a parabola on its side. And that's what a square root function is. It's technically just half the parabola on its side. All right, so the question here, what did they want to know? The window? Okay, so let's take this, grab our window. I like to move the cursor out of the way because if I grab it at just the wrong point, that black box that's blinking will be right over the number that I'm wanting you to see. It's not doing it right now, but I'm sure it will eventually. Okay, so there's my min and max for the x's and the y's. Okay, any questions on that? All right, so that is section 1.2. So tomorrow we're going to do the first part of 1.3, and that gets into y equals mx plus b, slope, parallel, perpendicular lines. A little bit of stuff some people already mentioned today. Okay, so homework for tonight, page 30, that's tomorrow night. So I'll get rid of that. Page 20 is for tonight. Okay, reminder too that I will be after school today, because tomorrow's the back to school night, so it's that's after school tomorrow, so it's easier if I stay today.